In this section, we're going to think about hypothesis testing. So we're still in the inferential statistics section, and we've talked about confidence intervals. So we can use what we observe in the sample to construct an interval that we think contains the population mean or the population parameter. Most of the time, it's going to be the population mean. So we take a sample, we calculate the sample mean, the sample standard deviation, we use a sample size, we set a confidence level, and we use that information to construct an interval that we think contains the true value. So what we're going to do now is to test claims about population parameters using what we've observed in the sample. And for some of these, we can use the confidence interval that we constructed before. But for other types of tests, we have to use a slightly different approach. So let's say someone claims they're talking about Microsoft, and they claim that the true average monthly return is 3.5%. What we want to think about is whether or not the data supports that claim. So if someone makes a claim, we're going to believe them at first. So we'll say, okay, the true mean is 3.5%. Does the data suggest it's actually something else? So if the data supports the claim that they're making, we will fail to reject their claim. If the data does not support their claim, we will reject the claim. So that's the big idea behind hypothesis testing. You say someone makes a claim, you see if that claim is consistent with the data. If it's consistent with the data, we fail to reject their claim. If it's not consistent with what we observe in the data, we can reject their claim. So when we're thinking about hypothesis testing, there's a null hypothesis which is claimed to be true. So in this case, the null hypothesis would be that the true mean is 3.5%. The alternative hypothesis is what we're seeking evidence for. So if the null hypothesis is equal to 3.5%, the alternative hypothesis would be not equal to 3.5%, because it has to be the complement. When I say complement, I mean the opposite of the null. So if the null is equal, the alternative has to be not equal. Later on, we'll see the null could also be greater than or equal to. In that case, the null would be less than, because less than is the opposite of greater than or equal to. Okay? So we're going to assume that this claim is correct, and then we look for evidence that it's equal to some other value. So why might the sample mean different from the population mean? So if we go back to central limit theorem, if we have large random samples, the mean of the sampling distribution should be equal to the population mean. So if the true mean is equal to 3% and we take a large random sample, our sample mean should be a number that's really close to that same value. So we need to think about why we might observe something different than what is claimed to be true. So let's say we believe that mu is equal to 10. Why might we expect it to be something different? We never expect it to be exactly 10 because it's continuous. 10 is one outcome of an infinite number of outcomes. So we would never expect it to be exactly 10, but we would expect it to be close to 10 if mu is the true mean and we have large random samples. So how close do we expect it to be? Well, it depends on the sample size. So if someone says the true mean is 10, and we take a sample of 2 observations, we may get a number that's wildly different from 10, even though 10 is the true mean. If we take a sample of 50,000 random observations, we would expect our sample mean to be closer to 10. So how close depends on how large a sample we actually collected. If someone claims the true mean is equal to 10, we may get a sample mean that's not close to 10, one, if the sample is small, or if 10 was just a terrible guess. Maybe someone claims the true mean is 10 when the actual mean is 50. Well, they made a bad guess. If they made a bad guess, then who knows what our sample mean should be. We don't really learn anything. But we'll probably reject their claim if our sample mean is 50 when they claim 10 and we took a really large sample. We can probably reject their claim. It could also be that our sample doesn't reflect the population of interest. So let's say we're thinking about the average average height of a WKU student. I don't know why we'd ever care about the height of a WKU student, but let's say we want to know the average height of a WKU student, but our sample only includes basketball players. Well, we're going to get a number that's much larger than the true mean for all WKU students because we have a poorly selected sample. We're sampling the tallest people on campus when we're trying to estimate the average of all people on campus. We also expect some sampling variation. So if you look back at this sampling distribution right here, the true mean is 3, but in some of these samples, we got a number as small as 1.5 and as large as 5. So just natural variation could lead to an outcome that's different than the number that they're claiming to be true. So in this case, we know the mean is 3. We know that's the true mean. Sometimes we get numbers smaller than that. Sometimes we get numbers bigger than that. But the average of these samples is the true value. But when you're doing hypothesis testing, you only get one sample. That's all you get. Because you take one sample and you use that to test, and that one sample could have been this really low value or it could have been this really high value. But notice, if we have large enough samples, we expect any of those random samples to be pretty close to the true value. So just natural sampling variation can cause us to have a sample mean that's much different than the actual population mean. So what we're doing with hypothesis testing, we want to know, again, we're assuming in what we do here that we have a random sample from the population, so it actually does reflect the population of interest. We want to determine if the difference we observe is because their guess was wrong, or if what we observe, or if what they claim could be reasonable based on natural sampling variation. So is the difference that we observe expected based on the sample size and the sample standard deviation, or is it different because we actually believe they're incorrect? So there are 3 ways to set up the null and alternative hypothesis, and there are only 3 things we can test. We can test, someone can claim that the population parameter is equal to some value. If they claim that it's equal to some value, so the null hypothesis is that mu is equal to that particular value, the alternative is that it's not equal to that particular value, we can reject this claim 2 ways. So these shaded regions right here are what we call rejection regions, and this is the t-distribution. So that t-distribution that we talked about for confidence intervals, we're going to use that again. So if you claim that mu is equal to some value, I can reject that claim if what I observe is sufficiently greater than what you claim or sufficiently less than what you claim. So that's what these rejection regions are. So these t-criticals are going to determine how different it actually needs to be before we can reject the claim. But if you claim equal to, I can reject that claim if what I observe is significantly greater than or significantly less than what you claim, and all that depends on the level of confidence and the sample size and all that stuff. But we'll work through specific examples in just a little bit. The other claim could be that the population parameter mu is greater than or equal to some value. And if you claim that it's greater than or equal to some value, I can only reject the claim if what I observe is significantly or sufficiently less than what you claim. So if you say the true mean for Microsoft is greater than or equal to 3.5%, and I observe negative 5%, maybe I can reject your claim. But if you claim that the true mean for Microsoft is greater than or equal to 3.5%, and I observe 5%, well, that's consistent with what you're claiming, so I can't reject it. So that would lead to a fail to reject. So if the null has greater than or equal to, I can only reject if what I observe is significantly less than what you have claimed. And the other case is you claim less than or equal to some number. I can only reject the less than or equal to if I observe something sufficiently greater than what you're claiming. So if you say the true mean for Microsoft is less than or equal to 3.5%, and I observe a 0, well, 0 is less than or equal to 3.5%, I can't reject your claim. But if you claim less than or equal to 3.5%, and I observe 10%, then maybe I can reject your claim, depending on my sample size and level of confidence. So these are the only 3 ways you can set up the hypothesis test: equal to, greater than or equal to, less than or equal to. And these regions are what we call rejection regions. So we'll talk more about those when we think about specific examples a little bit later. So when you're conducting the test, there's a basic procedure that you want to follow, and we're going to use this using the test statistic method because it's a little less complicated than the p-value method. I'll show you, we'll use the p-values later, but for right now we're going to think about the test statistic method, and this is the basic approach that you're going to use every time. So we're going to write down the null and alternative hypothesis. And when you write down the null and alternative hypothesis, it's going to look like one of these 3 things. And once you choose the correct one, you're going to label the rejection region and identify the critical value. For a two-tailed test, there will be 2 critical values because it can be a positive one or a negative one. For a left-tailed test, your critical value is going to be negative. And for a right-tailed test, your critical value is going to be positive. And this is actually incorrect at the bottom right here. This 0 should be right there, and this should be your t-critical. But your t-critical will be positive if it's a right-tailed test. Your t-critical will be negative if it is a left-tailed test. And we'll talk about specific examples later. Computing the test statistic. So this is the sample mean minus what they claim to be true divided by the standard error. So notice this s over square root of n, that's the same s over square root of n that we used in the hypothesis test. So this test statistic is going to tell us how far away the sample mean is in standard errors from what they claim to be true. So if you get a t-stat of 0, that means the sample mean is exactly equal to what they claimed to be true. If you get a test statistic that's positive, it means the sample mean is larger than what they claim to be true. And if you get a test statistic that's negative, the sample mean is less than what they claim to be true. We have to divide the difference by the standard error, and that's going to tell us if it's different enough. So these critical values right here are the benchmarks. These are the thresholds that we have to meet, and these are determined by the level of confidence in the sample size, nothing else. So this is the bar that we have to reach, your critical values. The t-stat is your evidence against the null hypothesis. If your t-stats are large in absolute value, so large positive or large negative, that's when you're more likely to reject the claim because what you're observing is further from what they're claiming to be true. So you're more likely to reject a null hypothesis when you have test statistics that are really large positive or large negative values. We compare that test statistic to the critical value. So if the test statistic falls in the rejection region, and I'll talk about this more, I'll do some examples by hand. These are the critical values. The bounds of these shaded regions are the critical values. If what we observe, if the test statistic that we compute falls inside of one of those regions, then we reject the null hypothesis. So if again, we look at absolute value. If it's a two-tailed test, if it is a one-tailed test, either you have one rejection region. If it's a positive critical value, so it's a right-tailed test, right here, your t-stat needs to be larger, more positive than the critical value. If it's a left-tailed test like this, the test statistic needs to be more negative than the critical value. So the test statistic has to fall inside the rejection region. And if it's a two-tailed test, it can fall in either one of these regions. So that's the basic procedure for hypothesis testing. And we're going to do this by hand, and we're going to do it in Excel, just so you see the process and understand what how it all works. So here's an example of a hypothesis test. So assume you have 127 monthly returns for Microsoft, where the sample mean is 1.89% and the sample standard deviation is 6.05%. Test the hypothesis that the true monthly return is equal to 3%. So let me grab a piece of paper. So I'm going to write this on a piece of paper over here, and then I'll turn the camera on in just a second. So our sample size is going to be 127. Our X bar is 1.89%. Our sample standard deviation is 6.05%. And we want to test, someone's claiming that mu is equal to 3%. So this is what we're claiming, or this is what we have. So we have a sample size of 127. The sample mean was 1.89%. The sample standard deviation was 6.05%. Someone's claiming that the true mean is equal to 3%. So do we have enough evidence to reject the null hypothesis? Is 3% sufficiently different than 1.89% for us to say we reject their claim? Because that's what they're claiming. And again, alpha is 0.05. So the way you would set a problem like this up, we're going to write down the null and alternative hypothesis. So the null hypothesis is that the true mean mu is equal to 3%. And the alternative is that the true mean is not equal to 3%. I think 3% was correct, right? Yeah, 3%. Okay. This is a problem where we have, this is a two-tailed test. So this looks like this problem right here. So we know we're going to have two rejection regions. So since we're testing this at 95% confidence, that means our alpha is going to be 1 minus 95%, which is 0.05. So when we set up the distribution here, again, this is a t-distribution. This is 0. We want alpha over 2 in this side, and we want alpha over 2 here. So we know that this number right here, that area is 0.025, and this area over here is 0.025. This is going to be our t-critical, the negative value, the negative version, and this is going to be our positive value. So this is always going to be symmetric. So whatever this critical value is here, this one over here is going to be the exact same thing. So this is t-critical, the negative value. This is t-critical, the positive value. So we have to do this using a function in Excel, which is a relatively straightforward function to use. So I'm just going to pull up just a generic sheet here and show you how we actually estimate these critical values. So this is going to be, so we're going to have our confidence level and our alpha. So this is going to be 95%, and this is going to be 1 minus that. So alpha is this. So to find the critical value, So I need to find the t-value such that the area to the left of that is 0.025, or that the area to the right of that is 0.025. The area to the right of the positive value of t is 0.025. Since this is a two-tailed test, there is a faster way to do this. So our t-critical for two-tail is going to be equals t dot inverse two-tail, because this is going to give us the t-value for a two-tailed test, so we don't have to divide alpha by 2. It saves you one step. So the probability is going to be alpha. The degrees of freedom is always the sample size minus 1. So since we had 127 observations, our degrees of freedom is going to be 126. So we're going to round that to 1.98. So 1.98. The reason why that number is important is that's the number that will identify the rejection region. So this is 1.98 and this is negative 1.98. So if the test statistic that we calculate using the sample mean, the sample standard deviation, the sample size, and what they're claiming to be true, if that is more negative than this or more positive than this, we're going to reject the claim. So let's calculate the test statistic. So our t-stat, remember, is x bar minus mu, what they're claiming to be true, divided by s over the square root of n. So that's going to be equal to 1.89% minus 3% divided by 6.05, and that's divided by the square root of the sample size. So that is the test statistic. And I already have that calculated in the notes. Right. So we wrote down the null and alternative. We found the critical values using that method in Excel. The test statistic that we get here is negative 2.07. So the test statistic, I didn't want to do this math by hand, is negative 2.07. So we have to compare this negative 2.07 to the 1.98 and the negative 1.98. We know that negative 2.07 does not fall in this rejection region over here, but does it fall in this region over here? So these numbers get more negative as we move to the left. The threshold is negative 1.98, and we're over here at negative 2.07. So negative 2.07 is in the left shaded rejection region. So since negative 2.07 is somewhere over here to the left of the negative 1.98, we reject the null hypothesis. Okay. So we reject. So, and the reason we're rejecting the null hypothesis is that their claim is 3%. We're looking for evidence that it's not equal to 3%. And the test statistic that we computed says we have enough evidence to say that they are wrong. With 95% confidence, we can reject the null hypothesis that the true mean is equal to 3%. So we reject the null hypothesis. So I want to make one simple change here. We're 95%, we reject their claim with 95% confidence. But what if we repeated the problem at 99% confidence? What if instead of confidence of 95%, we did 99%? Well, in that case, the critical values are now 2.62, negative 2.62. So if we're going to do this at 99% confidence, our rejection region is now 2.62 and negative 2.62. So these are the rejection regions. Our test statistic doesn't change. It's negative 2.07. Notice we're not in the rejection region. So in this case, it would be a fail to reject. So even though we have enough evidence in our sample to reject their claim with 95% confidence, we do not have enough evidence in our sample to reject their claim with 99% confidence. So the outcome of the hypothesis test depends on the level of confidence that you have, the sample size, the sample mean, the sample standard deviation. If you change any piece of that, the outcome could change. But once you have your sample, the sample size, sample mean, and sample standard deviation are fixed. You can't change those once you've collected your data. The only thing that you can change post-data collection is the level of confidence that you choose. So in this case, with 95% confidence, we reject the claim. But if we were to increase the level of confidence to say 99, we fail to reject the claim. So a couple things to keep in mind with when you're doing hypothesis testing. You can use a confidence interval to test the two-sided hypothesis. So we could have tested this hypothesis using a confidence interval. And let me show you how to do that. Let me show you just real quick how you would do that. I'm going to use the little tool that I built for confidence intervals. Oh, looks like it's already up. So I'm going to build my confidence interval using the information that we have in this problem. So our sample size was 127. Our sample mean was 1.89%, and the sample standard deviation was 6.05%. So the confidence interval that we get for this problem with the 95% confidence interval is 0.828 to 2.952. So we're 95% confident that that interval contains the true mean. The claim that this person made does not fall inside of the interval. So if you claim a value to be true and it's not inside the interval that we think contains the true value, we're going to reject it because 3% is out here to the right. So we're going to reject your claim at 95% confidence because you're claiming 3% and 3% does not fall in the interval. But notice what happens when we go to 99% confidence. The interval got wider. 3% is now inside of the interval that we think contains the true mean, and we fail to reject. So if the number that they claim to be true falls inside of the confidence interval, that means what they're claiming is consistent with what we're observing. We fail to reject. With 95% confidence, what they claim to be true is not inside the interval, so we reject their claim. So whether you reject or not depends on how confident you want to be. If you're okay not being extremely confident, maybe we're at 95, we reject. If we went down to 90, which is also somewhat standard, we would also reject. If you're 95% sure they're wrong, you're also 90% sure they're wrong, but it doesn't go the other way around. So that's how we can use a confidence interval for a two-tailed test. When you set up the null and alternative, just make sure you set it up correctly. Make sure you label the rejection region correctly, because this null hypothesis is only relevant when what we observe is less than what they claim to be true. If the sample mean is consistent with a null, you automatically fail to reject. And that's what this is saying as well. So if they're claiming greater than or equal to 5 and you observe a 10, well, that's consistent with what they're claiming. If they claim 10 or less than or equal to 10, you observe a 5, that's consistent with what they're claiming. So make sure you draw the distribution, write down, shade the rejection regions, and it'll help you avoid some silly mistakes. So I'll show you, I'm going to walk through a couple more examples in a separate video with the left tail test, right tail test, and show you a few more examples. And then I'll show you how to do all of this in Excel.